Hi, my name is Martin Lindquist, and I'm an associate professor in the Department of Biostatistics at Johns Hopkins Bloomberg School of Public Health. I'd like to take this opportunity to welcome you to Statistical Methods in Functional MRI. As the name indicates, we're going to focus on functional magnetic resonance imaging, fMRI, a non-invasive technique that allows for the study of brain activity. In recent years, there's been an explosive growth in the number of studies performed using fMRI, and the field that's grown around the acquisition and analysis of fMRI data is interdisciplinary in nature and involves contributions from researchers in numerous fields. These include neuroscientists, physicists, psychologists, engineers, statisticians, and many more. The analysis of fMRI data is an example of what is popularly referred to as a big data problem. These types of big data problems have revolutionized the field of statistics in the past decade. And in this context, the data is not only large, consisting of millions of data points, but also has a very complex correlation structure in both space and time. Statistics plays a crucial role in understanding the nature of the data and obtaining relevant results that can be used and interpreted by neuroscientists. In this class, we'll explore the intersection of functional MRI and statistics. We begin by discussing the structure of fMRI data, how it's acquired, and the images are reconstructed. In these early lectures, you'll quickly become aware of the truly interdisciplinary nature of this field, as this material will require us to discuss matters from physics, mathematics, signal processing, and more. We'll continue by discussing the signal and noise properties of the acquired data and the multitude of pre-processing steps that need to be performed before we're ready for statistical analysis. The subsequent statistical analysis, which is the main focus of this course, will deal with data acquired from both a single subject and groups of subjects. We'll focus on trying to determine regions of the brain that are active during a specific task, determining how different brain regions are connected with one another and how they communicate, and using a person's brain activation to predict their response or disease status. Each of these problems are complicated by the massive nature of the data. In this class, we'll address all these problems and more, and by the end of the class, you should have a solid understanding of fMRI and the role statistics plays in analyzing and interpreting the data. If you're a newcomer to the field, I hope this class will whet your appetite for this exciting area of research. You should gain a basic understanding of the types of problems we can address using fMRI and how statistics can help solve them. You should also get a solid grasp on the nomenclature used in the field, which will help you read research articles. If you've previously worked in the field, I hope this class will help demystify some of the statistical tools commonly used. We will seek to make the statistical analysis of fMRI data less of a black box endeavor and put the important statistical considerations made during the analysis into the forefront. Without this knowledge, it's very difficult to properly interpret the results of your study. Throughout the course, I would encourage you all to make good use of the course discussion forums. This will be the way in which you'll be able to communicate with your fellow students and with me. They provide a good avenue for you to post links to articles related to the course content and further discuss matters that are covered in the lectures. So once again, it's my great pleasure to welcome you to this class. I'm really excited about the opportunity to teach this material to so many new students at one time. So without any further ado, let's get to work.